Start. Okay, so we will wrap up the discussion today. So basically the idea is to review, discuss conservation laws, classical soft theorem as conservation law, something that we started yesterday discussing. And then finally discuss, at least have some discussion on the corresponding structures in quantum field theory, so quantum gravity. So we'll look at factorization theorems in of S matrix as and I'll put a question, like a quote here, because as we will try to, at least I will try to summarize what things are not completely understood in the quantum realm as word identities. Okay, so just to quickly recall where we ended last time was that I think that our final discussion was the following, that we kind of try to motivate that if you consider, so please ask if something is not clear. So I'm just, because of lack of time, I will try to go a little fast with this, what we did yesterday. So the idea was that there was a natural generalization of, okay, first there were the symmetries. So let me quickly recall. As we saw that there is a infinite dimensional symmetry group which is on the space of solutions of asymptotically flat spacetime, and that acts on it acts on scri plus union I plus, or equivalently scri minus union I minus, and this symmetry is generated by two sets of vector fields. One set of vector field which is parameterized by a function on a sphere, and the other set which is parameterized by smooth vector fields on a sphere. And we saw that we call this super translation, and this one super rotation. And we discussed yesterday how they act on both null and time-like infinity. So that was a part that for the super translation we discussed that how we can extend the super translation symmetry also to time-like infinity. So we if you remember, we defined from F this vector field xi mu at I plus, which was parameterized by F using this Green's function technique or something. So if you have a question, please ask, because I just will not write down all the equations for this today. And then finally the point that where we ended was that there was a natural motivation for defining the charge associated to super translation, total charge associated to super translation in the future, and that charge was, I'll call it Q plus F plus, which is integral over the sphere at u equal to minus infinity and similarly for the minus for the total charge in the past, there was a natural candidate which was such that it reduced to total mass and total linear momentum for appropriate choices of these F's. Okay, so this is where is that okay? Okay, and then based on earlier work in electromagnetism, Karthik, Prabhu and others showed that there is a natural, at this point, as we discuss, F plus, F minus are independent, and if they are independent generators in the past and the future, then we can't really talk about their conservation, etc. But you see that if you take F plus to be global translation generators, then they are antipodally identified. And so based on that, there was a natural motivation to consider that, let us consider a class of functions where F plus and F minus are same function, simply antipodally identified. And this was proved explicitly by Karthik, Prabhu and others. and based on their proof, they further showed that in any theory of gravity, this is equal to this. So once you do this identification, in the same paper they showed that how these two charges are conserved. So then this is a quite a remarkable fact that we have infinitely many conservation laws in any theory of gravity. Yeah.
Are you going to talk about the quantum version of these charges?
Yeah, I will go very fast in the classical maybe. So what? Let me do one thing. I'll do the following. I'll first do I will try to show how this statement of conservation law is same as the displacement memory, and then quantize it, and then go to the super rotation part in after that. Okay. So so now basically the statement is the following, and it's a very simple statement that remember this m is like basically the mass density at a point on a sphere, and so one can use Einstein's equation to solve this in terms of the free data. So if you recall, yesterday we had a long discussion on the free data at Scry, and the free data at Scry is CAB, QAB, CAB and DAB. Right? And if you have massive sources, I'm only right now looking at the future. Everything I'm saying should be true also in the past. And if you have massive sources, then you have fields in the future. I'll just call them matter fields, phi matter. And we gave an example of how this field look like at time like infinity yesterday for free massive scalar field. And now the point is the following, that Einstein's equation tells us something very simple, that if you consider dou u of m plus u theta phi, then that turns out to be equal to the following. I will write it. The stress tensor of gravity at u theta phi plus a term which is a bit pesky term, which is okay. But maybe, by the way, this d is the free data, and I don't want you to confuse this d with just two indices on the sphere with a covariant derivative on the sphere. Okay, so that's just this is a consequence of Einstein's equation. Near Scry plus. So if you just take Einstein's equation and expand them in 1 by r, and you see that one of the equation that pop out, and more precisely this equation pops out of the equation. For example, if you have Einstein theory, then the equation is GUU. If you look at this equation, GUU equal to TUU. That equation really reduces at large r to this equation. Okay, that can be explicitly checked. And now based on this, you can obviously see right that m plus at u equal to minus infinity is integral of this minus integral of this plus m plus at u equal to plus infinity. Is that yeah? And so now the statement is that we may worry what this quantity is, but of course physically you can see that, at least without any analysis also, this is the total mass which lives at u equal to plus infinity, which is a sphere here, and so that means that it must be related to the massive particles which are leaking out. Right, so we can. I hope the argument is persuasive, but because the detailed analysis is a little more complicated. But I hope it's clear what I'm saying. So based on this, now we can rewrite this charge in terms of our free data, both the free gravity data and the free matter data. And that charge, I will just write the final result. So Q plus F plus is equal to. So in principle, this TU can also have contribution from massless fields. If you have other massless fields except gravity, just for simplicity, I am assuming that I have only gravity and other matter fields which are massive. Okay, but nothing changes if you include. So that's why I wrote it as. I wrote it as TUU grav because I am assuming there are no other massless particles in the theory. So then this, if you do this, you just integrate with F, and the final result is actually quite simple. So it turns out to be minus integral this I will explain this notation I made, which I have not, I think, introduced yet. Okay, so this is just the volume on the ADS3 on the hyperboloid that we discussed yesterday. So this is the explicit expression for the super translation charges in terms of the free data. Okay, because this can be expressed in terms of the Fourier modes, which are the free data for the matter fields. And so everything now we have written purely in terms of the free data, where this NAB is simply defined as dou u of CAB. So is there any question about this? So now once we have this, we can, why is this useful? This is useful because free data is up to us, so we can actually check what this thing implies in any scattering, right? I mean, in the sense that I provide for you data in the past, then I know data in the future, and then I can actually explicitly go and check whether this conservation law is satisfied or not. And now the final statement is that if you do this, and DAB does not enter anywhere in this, and what is remarkable is that DAB will also not enter directly in the super rotation flux, but in a very in a subtle way. Yeah. So so now that's it. So now this actually, the point is the following, which is so let's start with some data at cry minus. So let's say that, just for simplicity, we say that in the past at cry minus, our free data, which is QAB, let me put C minus to indicate that it is the thing in the past, DAB, this data, I am specifying this data, and the data is unit sphere metric and 0 shear and 0 D. Actually D, as Aninda mentioned, D does not appear in this, so it doesn't matter what D we choose. And if you remember, D satisfied the equation that it was U independent. It was a static mode anyway, but just for simplicity I am doing this. So you choose this as your as your free data, and so that means in the past we only have matter. We have no gravity in the past, and so this matter comes, it radiates, it scatters. This is our picture, and then it will also radiate. And if you just stare at this, so that means what it is telling us that this thing is equal to same thing in the this thing in the future is equal to the same thing in the past. But in the past, all these terms are zero. Sorry, this is same as this. I should have erased this. So in the past, these terms are zero. Is that clear what I am saying? Because I have chosen my no incoming radiation, and so that means in the past we only have the matter contribution, and so the conservation law really looks like. So please ask if something is not clear. I'm just going to write, instead of writing down, just tell you what we will get. This term in the future is equal to this term in the past minus sum of these two terms in the future, right? That's what. So now let's look at this term. So I'm writing this term on the left hand side and everything else on the right hand side. Is that okay? So then let's focus on this term, and this term is simply integral du dA dB f NAB, and f is of course u independent. And now you see what is this, because since f is u independent, the sphere integral I can do outside and the u integral I can do first. But this u integral is just, if you go to Fourier space, this is just a zero frequency component of the your free data NAB, because this is dou u of CAB, so it just gives us a zero frequency component. And so now you trust me from this that the answer we find if you do this is the following. um, equal to everything which is coming from this term in the future, this term in the past, minus this term in the future, minus this term in the future. And it turns out that if you simply now express this in terms of the incoming matter stress tensor, this vector field is, remember, determined by F. So this is some algebra, but when you write this whole thing down, it turns out to be, you can show that this is equal to okay, let me not write it out. So there is the total, yeah, what I said, okay. All the terms difference. So term in the past, term at I minus, minus term at I plus term that's cry plus, and all terms which are quadratic in the fields, right? That's the conservation law that we have found. And the statement is now that this is precisely the displacement memory. The reason being that if you just stare at the displacement memory, it was if you remember what the displacement memory was, it was simply so the claim is that this statement that we have written down, which looks very different than what we had written down as a displacement memory, but this is nothing but the displacement memory written in a specific coordinates instead of Cartesian, the sphere coordinates. So what I mean by this is simply the following, that if you look at remember what the displacement memory formula was, it was the following. Because remember, displacement memory is the pole in omega, so you take the residue like this, and this turns out to be equal to summation over all incoming plus outgoing particles, or other, okay, maybe I'll be explicit, all outgoing particles minus similarly all incoming particles and then plus the nonlinear term. If you have radiation in the future, then there was the nonlinear, the Christodoulov memory term, which was integral right, if you remember this. So now the point is that you now do one thing, going from here you go to the sphere coordinates, and so write everything in terms of sphere coordinates. And so you do, so let's say that to go from Cartesian to sphere coordinate, we have some projector. Oh, sorry. Okay, so if students, if you have not seen this, you will simply change the coordinates from r theta phi to x, y, z to r theta phi, and look at the theta phi component. So that's just this Cartesian to sphere transformation, and that will then map these quantities to some overall. So this stuff is function of the matter at I plus, matter at I minus, and this is the gravitational radiation at I plus, and all these mu nu's are projected out into the AB components. And now you just integrate both sides with dAdBf, and then you see that actually you can explicitly check that this is what you find from here is exactly that conservation law. So this is sorry, I couldn't go into all the details of the algebra, but they can be found in this book of Strominger, for example, that about this statement. I mean, going from this conservation law statement to the displacement memory. So, is there any question, at least of the structure? And so this validates the fact that super translations are not only symmetries on the space of solutions, real super translations, but they are also symmetries of gravitational scattering in 4 dimensions. No, that's the point, because I just as an indication told you that the equation for the m comes from this, but you can add any higher derivative terms here, let's say we all package all of them like this. If you take large R limit, they all drop, so it doesn't matter. Yeah. So it's a statement in 4 dimensions and for any theory of gravity. So this part of the story, I would say, is the cleanest statement, as far as the cleanest in the sense that everyone will agree that these statements are true at any level of rigor. There is a conservation law for supertranslation in gravitational scattering, and that conservation law gives us the displacement memory, including the nonlinear displacement memory effect. Okay, so now I'll just first, before going into the log, understanding the log universality in terms of symmetries, as Aninda said, let's actually jump to quantum first and try to find if this is so the question we want to ask is that if this is a symmetry of classical scattering, is it anomalous in quantum theory, or is it still a symmetry of the quantum S matrix? And this statement is of course tricky because of the fact that in 4 dimensions there is no S matrix, and so we have to really be careful how to ask this question. So the question we want to ask looks a bit paradoxical, that what is the symmetry of S matrix is supertranslation a symmetry of the S matrix in D equal to 4 dimensions? But the statement doesn't make sense because this object itself is 0 in 4 dimensions. So the S matrix itself vanishes. And so that's why the statement looks empty. That what do we mean by having a symmetry of an operator which is 0? And the reason, of course, this is 0, one can see it by explicit computations. But the physical argument simply is that if you start with any particles, any in state, and then you say that okay, what's the probability that I get a fixed out state? That's what S matrix is supposed to give us. But there is always a finite, start with any in state, there is always a finite probability that you can emit arbitrarily soft gravitons. So that means that, but the total probability of getting all out states is 1. So that getting the probability for a fixed out state, where you fix the out state, is obviously 0, because there are infinitely many out states which are possible. So this is an intuitive argument as to why S matrix vanishes. And technically the reason that happens is that if you go beyond tree level, then you will see that the S matrix looks like some e to the phi, it factorizes into something like this. This is shown in Weinberg's original paper, where phi goes to infinity because of infrared divergences in the at loop, and so that this S matrix vanishes. So that's a technical proof, and this is a more intuitive argument. So now we are saying, okay, then how can we even ask this question? And to understand this, how to ask this question, we should look at the S matrix.
Lack of knowledge.
No.
So you have something that goes to 0, but then at higher loops I would have thought that there will be UV divergences. So those don't cancel.
They don't cancel. So I'm assuming that we are in an effective field theory with a cutoff. Otherwise, of course, gravity we are in trouble anyway. So we are in some, as you right. I mean, a theory of gravity means always some UV cutoff is there for us. So they don't mix in flat space in De Sitter. Maybe there is some mixing, as Polyakov claims. Okay, so but still we can go ahead and try to ask the question as precisely as possible. And it turns out that contrary to the expectation, this actually has a very precise answer. And the secret, the key lies in forgetting asymptotic symmetries for a second and simply looking at the amplitudes. So because S hat is not well defined, because it's infrared divergent, we have to regulate it. So first let's do one thing, let's do a brute force regularization. So I'm going to replace this with S hat epsilon or S hat delta, where delta is the infrared cutoff. So please ask if something is not clear what I mean by this statement. So what I mean roughly is that whenever you have any diagram like this, for example, you have two particles coming in, and they are these are wiggly lines are gravitons, and you have some integration over the loop momenta, and you typically have things like this. Suppose this is L, So you will have stuff like 1 by L square. So here, over when you integrate this, your mod L should be bounded from delta to infinity. So that's what we mean by the cutoff. So you do all the calculations where you take the lower limit of loop momentum, not 0, but some arbitrary ad hoc cutoff, and then do the computation. So of course it's not a physical thing to do, and our hope is that only things we should take seriously is which survive in the limit delta going to 0. So that's the logic of what I'm saying now. So we take this S delta and do the following. We look at n plus 1 point amplitude, where you have some incoming particles, some P1 to Pk, and they go to outgoing particles. They can be any particle, scalars, fermions, whatever you want, even gravitons, but they have finite momenta, Pk plus 1 to Pn, and one graviton with some helicity h. Okay, is that clear what we are computing? So we take this, but of course then there is a cutoff here that we have to put, otherwise this won't make any sense. And so I compute this, and now what I do is I look at this quantity at a finite cutoff and do expansion in the frequency of so this k mu is omega some unit vector. So I do expansion like we did in the soft radiation theory, in the classical radiation theory, expansion in omega. So when you do H is a helicity, sorry, of the graviton, helicity of the graviton.
So all those other particles are not gravitons?
No, I'm just suppressing. They can be anything. Right now, let's take them to be, I'm just not writing. You are right. I mean, in general, they would have helicity and any other quantum number. Just because what I'm about to say doesn't depend on those quantum numbers, so I'm not writing them.
I'm just saying that.
Yeah.
Is there any condition?
No.
Those other guys are. Is there a statement that they're massive or something like that?
No. There's no condition. There's no condition. Yeah. So they are any particle. But the only difference is that we are doing a expansion in the. We are saying that we are increasing this amplitude when the energy of one graviton is much less compared to the whatever the scales are in this other scales are in the problem, energy of particles and center of mass energy and everything. And so when we do this expansion, then you see that what you find is okay, so that's the, this is a very direct computation that follows some gauge invariance, and you can find this in this, any of the original works of Weinberg, for example, or even older works actually. But anyway, this is a simple computation that you can do. I should say there is a omega here and plus higher order terms like log omega. Okay, so that's the statement at the level of finite delta. But now you notice that what this tells you is that if I consider the ratio of these two quantities and then take the limit delta going to 0, this ratio is infrared finite because there is no delta here in this side of the story. So this quantity is called Weinberg's soft factor and typically denoted as which is a function of all the momenta and the angle. Okay, so that means that even though the S matrix is not well defined in 4 dimensions, the ratios of these two particular amplitudes is well defined, and that ratio is, if you do an expansion in omega, then the leading term is a universal term which depends only on the momenta of the particles. Is this okay? So now our goal is to understand if this statement, which is regulator independent, can be understood in terms of the symmetry of the regulated S matrix. That's the logic that we want to So that's the context in which we should understand what it means when you read claims that super translation is a symmetry of S matrix. It really means in this context. So the idea is that because the ratio of these two amplitudes is independent of the detail of the notice that this is same as the universality we saw in the classical scattering, right? That the n plus 1 point amplitude divided by the n point amplitude doesn't care about what the scattering actually is. That ratio only depends on the asymptotic quantum numbers of the particles, right? So this is the universality, and so we want to understand the origin of this universality in the quantum theory, exactly like what we did in the classical theory. Okay, and so obvious way to do is to quantize this super translation charges, but that's not very hard because everything is now written in terms of free data, so we can just do it. So now we want to ask the following question, that if I consider the regulated S matrix S hat delta, and then consider, I will explain what I mean. So we have this classical super translation charges. So now I'm just going to put a hat, I will tell you what it means. Intuitively you should understand why going from classical to quantum is not non-trivial, because at infinity all the fields are free. And so then, quantizing free fields we know how to do, and so that, you shouldn't be very puzzled by this quantity. But what we want to ask is that if we consider this statement, so claim, or rather question, is this statement, is limit delta going to 0 of this quantity, this statement, is this same as equation 1? Is this equivalent to 1? So if that is true, then we say that in this context, precisely in this context we should say that super translation is symmetry of the S matrix. Okay. So these words are not completely correct because there is no S matrix, but quantitatively what we mean is this statement right here. Is that fine? Okay, so now we just try to quantize, but that's not very hard because QF, I will write a bit fast. So QF was a function of, let's see what fields it was a function of classically first, and then we will try to quantize these fields. So it was a function of this dou u CAB and the matter fields at I plus and I minus, right? So phi matter at I plus. Let's look at in the future. Right? It was only function of these two fields, if you remember. And so now the idea is that if we can quantize, we know how to quantize this, because as yesterday we saw that in phi at I plus was so phi at some point, rho theta phi was same as the Fourier mode, which was parameterized by rho theta phi plus Hermitian conjugate for a scalar field, for example. So that means that we know how to quantize this because that's just quantizing free field. And now the only thing we have to understand is how to quantize C, because that we have not discussed yet. But that is not very difficult because C is field at infinity, so it is literally related to the free gravitational field in the following sense. So let's just consider, I'm taking a slight detour, so our now only thing we want to understand to complete this analysis, the only missing thing is how to quantize CAB.
So the file that you're using is right by input, right?
I mean, yeah.
So but the CAB data is in
At Scry.
Scry.
Yes.
So and is there a
They are free.
Huh?
They are just free.
They are free fields.
They are free fields.
And so where am I supposed to think of these fields as living when you quantize them? Is it,
Exactly. So this you just think of them as living at the slice, which was a blow of I plus, for example.
So CAB.
No, not CAB. Only the matter.
Yeah.
CAB is living. CAB is a quantized, and that quantized field is living on Scry.
So now you're in union of I plus.
Yeah, we were always in the union because we needed both, right? No, Chetan had something else in mind.
No, that's what I have.
Okay,
I think, so that's a charge that you're constructing from fields that live in two.
At two boundaries. And so we had to look at the contribution of the total super translation charge in the future is a contribution coming from this boundary plus a contribution coming from this boundary.
Okay, I see. So you're basically adding the two charges in order to define the total charge.
Yeah, I mean that just came out of the analysis that the charge was first defined at this sphere, and then Einstein's equation told us that it was this charge plus that charge. So it's not like we, you see what I'm saying, right? That's what you, yeah. Okay. So let's try to understand how to quantize C. And to understand how to quantize C, so it is enough to consider free linearized fields because C lives at infinity, right? So as far as C, quantization of C is concerned, the interactions of H gravity doesn't matter. So let's consider a free field, H mu nu, as a function of u r theta phi. And we know that if it's a free field, we can simply decompose it into Fourier modes. Where this x is of course u r theta phi. Now you do two things. Now you take the limit r going to infinity of this and you project mu nu to AB, to the sphere coordinates, because that exactly, if you remember, will pick out for us CAB, which was the radiative data. And so when you do this, you will see that what you find is precisely so when you take this limit, you get, I'm writing the final result, I will explain how we get it. So, I mean, asymptotically. Now, if you remember the expansion of the metric, the CAB term was a coefficient of R. So that clearly tells us that CAB is precisely this, can be written in terms of the creation and annihilation operator of a free graviton, and this is the transcription. So CAB at u theta phi is equal to this integral only over energy, not over all the components of K, where the Fourier mode is localized at theta phi. And that localization simply comes because, as we discussed in one of the earlier sessions, that if you take large R limit, you pick a saddle, and that saddle gives you this kind of a localization. So now, okay, now we know we can quantize C in terms of the graviton creation annihilation operators and the matter in terms of the matter creation annihilation operators, which means I can just quantize this charge. Right, and then once I quantize the charge, where is it the charge acting? It is acting on the states of the so what do I mean now? So I have some quantized charge which acts on free states, because then we are simply quantizing in terms of free fields. And so that means I can now ask the following question: what is the action of my charge in the future on a state in the future at, let's say I have only massive particles for simplicity. So that's my state in the future, and it's of course a free state in the future. So I compute this quantity, and this quantity will give me some, clearly the stress tensor of, remember this has three pieces: stress tensor of gravity, stress tensor of matter, and there was a linear term in CAB. So the stress tensor of matter will just pick out the some eigenvalue from this state. The stress tensor of gravity will vanish because I am starting with only a matter state, but that's only for simplicity. And the other term, which was linear, if you remember, there was a term in the charge which was now you see that this CAB is a function of graviton creation and annihilation operators, and so clearly the creation operator will create a state, but it will create, because remember we are integrating over u, so this will create a zero, kind of a zero frequency state. Okay, so what it creates is, so I'll just write it. It is some eigenvalue depending on the matter momenta, which is can be immediately evaluated, plus a new term, additional term, which I'm going to write formally right now because it doesn't make sense as a state. So I'm just writing it like this. Yes.
So the charges, the contribution to the charge should come from basically from all the free data in the metric together with the field file.
Yes.
Side,
Yeah.
right?
Yes.
So so that the free data in the metric is basically all the QAB, CAB, DAB, etc.
Right.
But why was it that we have ignored DAB and QAB?
Because our charge, that's an excellent question, because our charge only it didn't depend on DAB.
The actual expression.
Yeah, actual expression didn't depend on DAB. And QAB, that's it's a sort of a choice.
And
Exactly.
it's a four-dimensional.
That's a just. It will depend on other data. Yeah. But yeah, I already mentioned. Other problems are there, but not the.
In this case, you will have to actually incorporate the DAB stuff also.
Yeah, which they have done in the even dimensions. So then I'm just writing it schematically. So please ask if something is not clear. So when a term like du NAB u theta phi, if you quantize it and you apply it on this state, on a vacuum state of gravity, it creates a state which I'm now writing. So it creates like a, but notice this thing, this is a kind of a pathological limit. You take the graviton state with energy omega and take some limit omega going to 0. So that's the action of, full action of my QF in the future on a state in the future. Is that fine? Okay. So now we want to understand the following thing. I take a state in the past, let's say P1 prime to Pn prime. I take my Q hat in the past. I have the regulated S matrix minus in the future. And now I want to ask this equal to 0, and if I now take limit delta going to 0, what does it give me? That's my question. So if it blows up, then QF is of course symmetry of 0 S matrix, and it doesn't help us at all. But if this gives us a finite result, then we are okay. And this one can check explicitly is precisely equivalent to the statement we wrote, which is where this is the polarization of the soft graviton. Okay, so I hope this at least this point is clear. So it is in this sense that we say that super translation is a symmetry of gravitational S matrix in 4 dimensions. So,
Can you just explain this rotation? What was happening here?
this I was just indicating what these charges schematically do to this state. So these charges, remember 3 contributions: the stress tensor coming from the matter stress tensor, then the gravity stress tensor, and this one pathological like this mode, linear mode. Now if I start just for convenience, I started with a state where the out state has no gravitons, only massive particle. But this is just to simplify our life. So all this state is defined at I plus, and so when this charge acts, the contribution which is proportional to the matter stress tensor will give you some function of P and the state back. But the term which is linear in CAB, that gives you this kind of a strange state, which is what people often say is we are inserting a soft graviton in a state and then taking the limit, studying it in a limit that the energy of the graviton goes to 0. So this state in this limit doesn't exist. It's because infinite wavelength state. But so that's the in the limiting sense, that's what we find. And the statement is that, okay, sorry, I should have said this. So the really the statement we find is the following, of course, because there is no omega. So if you write this now and just evaluate it, then you literally get this as your statement, and that limit omega going to 0, omega kind of stays outside and gives us a term here, and we get a ratio. Then we can take this limit, and this is equal to the Weinberg-Soft factor. Okay, so is there any question about this?
you are first taking data just to your
Yeah.
the higher order terms, for example,
Yeah.
that will divert.
Yeah, so that actually it's not very clear in the soft expansion. All the terms people have studied, they don't diverge. But I mean, you can take it the other way around. So it's yeah, all the terms we know so far, like the log and the higher ones, they all have good ratios. So that's I was a bit sketchy, but okay. I mean, sure, you can look at it. You can write it the other way. I'm saying this is not wrong. It is not known to be wrong, but okay, if it satisfies you, then we can write it like this. Yes. Yes, you can do dim reg, for example, exactly. You can do, instead of putting a hard cutoff, you can do dimensional regularization, and then this Weinberg-Soft theorem will not change. Because the point is that it doesn't really depend on anything except the emission of graviton from the external leg, this factor. So, all the dependence on the our regularization, they are in the part of the S matrix which is away from the emission of the graviton from the external leg. And that's why it gets factored out no matter what scheme you choose.
So when you said dim reg, you are talking about the dimensional regularization, which is
4 plus 2 epsilon. 4 plus 2 epsilon. Yeah, okay. So if there's no question, then but yeah, let me pause here, because this is the program of relating any event shape with symmetry of the S matrix really should go through this careful procedure where we do not have an S matrix, so we must always interpret the statements in this sense. Okay, so that's one point I would like to say, because it often doesn't come out in the papers which are written in this subject. Yeah, okay. So let's see. Yeah. No, we do. People often do.
basically means you're looking at somewhat lower intention.
Yes, absolutely. I mean, I think because obviously, as you know, the disadvantage of using hard cutoff is that you break Lorentz covariance. So people generally use dim reg even for IR.
So what is a good reference for this discussion?
This is. I mean, this is storming. This particular work. Oh, so I should cite. I mean, this particular work is. There are two papers. Strominger 2013, where he kind of put forward a proposal, and then there was a paper by Prahar, and I'm only talking about super translation, about identities, Strominger and others. That was 2014. But these papers were written where the external states are massless particles, and then with Miguel but it's not a big deal. I mean, it was just generalized this to in 2015, where your external states are massive. So if you really want to look at exactly this particular setup where you only have states at I plus, then that was something that we did in the. But I should mention that all of us, these papers, our paper, it was always cavalier about the IR issues, because in our mind we are saying that let's first understand symmetries of tree level S matrix. But the point really is that because the Weinberg-Soft theorem is an infrared safe observable in itself, if super translation has to explain its universality, it should be true for all orders in the S matrix. Yeah. Yeah. Yeah, D equal to 4. D equal to 4. Yeah. Yeah, that's a very good point, but I think that in the, when I said it, I realized you will catch me. I need to think about this, because in higher dimension, S matrix is infrared finite. So, no, okay, you are right, I take that back. What you are saying is correct. Okay, let me, there are two issues here which are a bit independent, but it's an excellent question. So, I must say I don't know much about higher dimensional S matrix, but let me tell you what little bit I know. So the point is that there are, of course, as you know, there are two types of divergences that we find when we have, say, gravitons or photons. One are what we call virtual infrared divergences, which come from loop momenta, and one are the one that I gave you this argument that, with any amount of as much low energy as you want, you can always emit soft gravitons. Now these divergences are absent in d greater than 4 dimensions. Okay, but so what happens? Sorry, I want to say. So what happens is that if you start with some in state and go to some out state, you fixed out state. So if it can have some matter particles and some gravitons also, but a fixed out state. If I just compute this, then this amplitude is finite in d equal to phi. Now you can ask, how can this possibly be? Because of the fact that the logic that I can emit any number of gravitons, that amplitude should be non-vanishing, and this I have to think now a little bit. I don't know if anyone Sachin. That is a Coulomb phase. That will be finite.
But that phase will be different in 4 and
that will be that will be finite. But the point is that
remember that is what was causing when you have, so if you have K1, K2, but
yeah.
you take K1, K2,
Yes.
Kn,
Yes.
n going to infinity.
Yes. Yes.
That gives you
Yes. Technically, it is correct. Arnab's point is that the intuitive argument we had that the real infrared divergence, the point that why the asymmetrics is 0, because there is always a finite probability to emit any number of low energy gravitons. So that argument fails right now. Okay, I shouldn't have said that. Thank you. Okay, fine. So
you have better argument.
yeah, no. That the phase argument is clean, but okay. But I don't know. There may be a way to. I need to think, Arnab, because when we integrate over the phase space in higher dimensions, the phase space measure is also different, and so I think that's the point. Yeah. Now I understand. So what is happening is that you see that if you are in higher dimensions, you will have mod k to the d minus 1, right? And then d minus 2. Sorry, if you are in d space-time dimension, and you see that if you emit like one, if you emit. If you are okay, let's say if we are in 4 dimensions, so what we get is like mod k square d mod k, and if I emit one graviton and if I look at the cross section, then it has like roughly speaking this mod square thing. So these things cancel, so there is no suppression coming from the phase space factor. But in higher dimension, this part will not change, but this part will change, and so actually the probability of emitting low frequency gravitons itself becomes 0. It don't remain finite.
That's the same as the original phase.
No, that's the virtual. So that's different. That's the virtual phase. That was the virtual divergence. So I was a bit sketchy. Sorry about that. I mean, I'm saying that when we compute this, when we compute in 4 dimensions the S matrix, we get a phase, and we get some part which has no IR divergence, and this is infinite, and that's why the S matrix 0. But this infinity comes from the virtual infrared divergences. Yeah. No. This is precisely coming from the virtual infrared divergences, and this is finite in higher dimensions, which is your question. And I think there is no pathology. So S matrix is finite in higher dimensions, and the argument also I think is okay, because probability of emitting soft gravitons is 0. It's suppressed with the energy in higher dimensions, of course. Thank you. Yeah, that was excellent. I should have thought properly. Okay, so I don't know, maybe I can, it's up to people. I mean, I can now end, we can have a discussion, and super rotation we can, yeah.
Argument should also hold for photons.
It's the same. Yeah. Okay, so if people are tired, I think people are tired, so we can forget about super rotation. Maybe I can provide references, and whoever is interested can study what happens. How do we understand the logs of theorem from this some sort of a regularized word identities again of these other symmetries that I talked about. So okay, let me just give you 2 references if you are interested. A couple of references. One is actually there are many. I will have to write. So okay, now we are in a truly discussion session, but I'll just give you some reference for understanding the log omega soft theorem as a conservation law. Oh, maybe let me, sorry. Can I take 5 more minutes, Anindra? So oh. No, I don't want to be more hated. So let me, sorry. I haven't, let me, rather than talking about the symmetry, let me talk about the amplitude part of the logs of theorem, because so far we only talked about the classical logs of theorem, and here there is a real mystery which is not entirely also understood, which is the following. So this was a work by Bishwajit and Ashok in 2018. And they showed the following. So they said that, I'm going to write the result and then we will discuss it. That if you consider again the same thing which we discussed, n plus 1 point regularized amplitude of say n particles, n hard particles and 1 graviton, which we are doing expansion in, and if you divide it by the regularized n point amplitude, then it has this Weinberg factor that we discussed, plus another factor which also is universal in the sense it depends on only on the initial and final momenta of the particles, and the direction of the graviton, and plus higher order terms. And now the point is that this factor is not the same as the, so remember this factor is same as the classical displacement memory, right? I wrote down a bit earlier this factor pi mu by pi dot n hat, which was the same as the classical displacement memory. But if you do the expansion of the amplitude at next order, this factor is not quite the same as the classical logs of factor. It has more terms, and those are a bit mysterious. So let me call this S quantum. And that is the one that we wrote down in detail, I think a couple of lectures back. So I'll call that classical, the expression that we wrote down. Plus more terms, and these terms I will write down just the structure of these terms because it is a bit different and a bit revealing as to why it's a bit mysterious also. So just to recall your memory that these terms had the following structure. You had to sum over pairs of particles where each pair was either in the incoming state or in the outgoing state. So if you remember this, we wrote down these terms, right? And now the point is that the new terms have the following structure. Sum over all pairs of particles. It does not matter if both are incoming or outgoing. One can be incoming, one can be outgoing. And the structure of the term is also a bit different, and it looks like it has some log. So it has and then everything else was as it was in the classical kind of factor. Okay, I will not write. I hope you remember what, there were terms like this, right? Okay, I will not bore you with more details. You can find expression in Ashok and Vishwajit's paper, but the important point is that it has a term which has some log branch cuts in this Mandelstam space of external momenta, and it is sum over all particles. But if you notice, there is no extra h bar here factor. So when Ashok and Vishwajit derived this in the amplitude, at the level of amplitude, this factor was the one that they then with the S cube derived in the classical theory, plus new terms, and these new terms are not quantum corrections in the sense of h bar corrections over the classical. So you can ask, how can we get this? And of course, the technical reason why this comes is the difference between causality in the classical and quantum theory. So in the S cube paper, if you study, of course, because they are doing classical radiation theory, they use retarded propagators. And just to recall, in a momentum space, retarded propagator has this kind of I epsilon. And but of course, as we know, when we study Feynman diagrams in quantum field theory, we will always use for all propagators Feynman, which will have structure like and so here, as is well known, that we can always, because the L0 has pole only in the lower half plane, you can always on the counter in the upper half plane, and you can just remove all the L0 poles. So that's why when S cube did the derivation, all the logs, none of the logs came from the L0 pole. But here there is no such choice because there's always L0 has one pole in the upper half plane, one lower half plane, and so that pole gives new contribution, which are these contributions. And so now so this is a little bit of a mystery in the sense that why naively, if I consider large momentum like astrophysical objects, and no one told me the S-cube result and told me that in the case of the displacement memory, I look at the Weinberg soft factor and that's my memory. If I use that idea, then this would be my tail to the memory. But actually it's not quite, because these terms are coming from these terms are not violate classical causality basically. So this is an interesting facet of this soft theorems, that in the classical and quantum theory they are not always the same, these soft factorizations. But this is the full infrared finite event shape in the amplitude, this quantity. And now the idea is that can we understand this from some conservation law, again in the same way we did for the super translation. And we do not know how to get this in gravity from what identity right now of any conservation law, but we have made progress in understanding how this factor arises from classical conservation law associated to this super rotation symmetries that we spoke about. So okay, maybe if you ask more I can answer, tell you more.
Let's say some kind of black hole is scattering.
Exactly.
So in that case, should you include this term?
No, you shouldn't include. Yeah, that's S-cube result, but you know, I mean, if you.
But if you take the scattering limit, the scattering, as a quantum scattering, like a soft theorem kind of calculation, you will get this term.
Exactly. Naively, it looks like you will get this term. So why should it cancel? Okay, we have some understanding, because your classical limit should remove always the Feynman poles, but this is the place where one has to be a bit careful. So we can discuss more. I mean, people have made progress in understanding classical limit of quantum radiation and showing that these terms go away, but they have done it order by order in perturbation theory. You see the important point about all these theorems are that they are totally non-perturbative. So to show this.
So it seems plausible, at least order by order, that it can be removed.
Yes, it can be removed. I mean, people have shown up to 2 orders that it can be removed, but there is no clear non-perturbative state.
Have a non-perturbative.
Yes. Yeah, so again, now in gravity, we have no understanding of, because we have not so what we know is that if you look at the conservation law for this super rotation in 4 dimension, the corresponding charges are such that they give you this term classically. Now if you quantize it, then we have not done the quantization to so we don't know whether quantization induces additional structure here. But in the case of QED, there is exactly the same pattern repeats in QED. So there is this, as you know very well, there is this quantum log soft factor for photon, which is the classical part and the quantum part. And here Miguel and I showed in 2019 that the conservation law that gives you the classical log soft factor, when you quantize it, the Feynman boundary conditions give you a new term in the operator, additional terms in the operator, which will produce for you this analog of these terms. But in gravity we don't know. But I must say that there are some papers which I do not understand, which claim that they get the whole thing. So I should mention that paper, and that's a paper by Laura Donne and Ruzziconi last year. And their claim is that the Ward identity of superrotation produces everything, but I don't understand the proof in the sense that their proof breaks down if you take classical limits. So somehow they have some quantum Ward identity but no classical conservation law, and that seems a bit pathological. Anyway, it's a confusing thing. So I would say that this part remains kind of not completely understood in gravity.
So are they saying that it's
No. They are saying they get everything, but their proof, their quantization is I don't understand, because they don't start with a classical charge at all. They just say that okay, they propose some quantum operator, and it seems to not have a good classical limit. So the logic would be that first we should have a classical conservation law which explains these classical observables, and then we should hope to quantize and get this. So now we understand how to get this from these diffeomorphisms, but we don't know. We don't have a complete story for all the terms in the quantum, in the gravity case. Okay.
Can you also incorporate poles? Because they're talking about poles. Can you find, is it robust enough? I'm not saying.
You mean the poles of the?
Yeah, bound state poles.
You mean the conservation? Is the symmetry going to tell you that there are bound states? No, because this is a because this is an asymptotic symmetry, so it only constrains infrared physics, right?
That's right, but the Molar operator, which is what you use to
Yeah, it has.
that knows about.
Yeah, certainly, yes.
So even though you are doing only scattering, analytically.
No. Yeah, absolutely, you are right that you can construct. I mean, you could do scattering, and you could just you could just.
If you restrict to physical momenta, then there will only be scattering.
Yeah,
But if you are
exactly.
continue,
Yeah, but I mean, I'm saying that those structures do not influence the infrared physics to the extent I understand directly, in the sense that if I'm looking at the low frequency radiation, it is insensitive to whether in a complex momentum plane a black hole formed or not. At least I don't see the presence of a bound state in the soft factorization theorems just at the level of amplitudes. Like even in QCD we don't see, right? QCD we have understanding of these factorization theorems very well now, but we don't see that the bound states will change the theorems. So I think, but the point you are raising is, that remind me, I should have said something that one should be very not super excited by these symmetries in the following sense, that the symmetries, as you can see, that even what are they telling us, even in their conservation laws are giving us soft theorems. So because these are asymptotic symmetries, they are only acting at infinite distance, they are only constraining the infrared physics of the theory. So they are not like global symmetries. So one shouldn't take them, one shouldn't hope directly that they would teach us something about the physics in the center of the scattering. At least so far there are no indications that. So I'm saying that because these are, even though there are infinitely many charges for super translation, super rotation, you may think that makes the theory, it may very much constrain a gravitational scattering, but because they are asymptotic as opposed to global, and so they constrain infrared physics, not the hard scattering. They don't tell you what is AN. I mean, they give us a ratio always, as far in the sense that at the level of amplitude, this void identity is always giving us these coefficients of this ratio in the soft expansion, but they don't tell us what this guy is. So just to put it in context, that even though they are infinite dimensional, they don't give much insight into the the nature of quantum gravity away from the infrared.
Right, but I think that one could say with ADS CFT2, for instance, a CFT2 has infinite dimensional symmetry. I think that's actually a global symmetry, right?
That's a difference.
It's a global symmetry of the dual theory.
That's a difference.
And in the bulk, you will still are kind of mysterious. I mean, that's I think what you're saying.
Yeah, but in 3 dimension is a bit strange, right? I mean, so.
No, three or not, but my point is that
because
symmetries for me in the holographic theory are genuinely global. Okay?
No, they're global symmetry means certainly they are symmetries in the sense they give us conservation laws, but as you can see.
In ADS3 CFT2, like asymptotic symmetries are basically the symmetry of the dual theory. They are genuine global symmetries of the dual theory.
Yeah. So here.
In that sense, I mean, we don't know the dual theory here.
Yeah.
So in that sense, we don't have operational use for it.
Yeah.
But nonetheless, I would treat them as the same level.
No. They will be global symmetries of the dual theory if you have a dual theory. But from the bulk perspective, they constrain only the infrared physics. So if you construct a dual theory based on only these symmetries, it is difficult to see why they will give us a dual of the. It will probe the. You see what I'm saying? It will probe the hard part of the.
I was just, you mentioned that it's not quite global symmetry.
No, you are right. They are global for the dual theory, but unlike the
we understand.
Yeah.
So just homogeneous quantum matters.
Yeah, they are boundary as they're like in ADS CFT, right? They are on the boundary, but the from the bulk perspective, they are symmetries which are asymptotic. I mean, this is the point that they are only constraining soft physics. So yeah.
I mean, the other Viras's symmetries on this scale, right? Which
Yeah, this diffeomorphism. No, but that's what. Yeah, either Virasor or diffeomorphism. Yeah.
singular.
Yes, the singular part.
I thought that was somehow, does that play a role in celestial programming? I don't know.
Yeah, I mean, we have an expert. I don't know much about celestial holography. I think it plays important role. Yeah.
I thought that was that strength certain couplings in the. So I would use the word.
No, but that's my point. That they will not. If you give me a theory like Riemann plus R square, these cannot constrain them. These cannot distinguish them,
But
because
I think I his point of view in the sense that I think he's saying that that's in some sense a bulk reconstruction question. If you are thinking of ADS3 CFT2 as a quantum theory, I think these are part of the global system.
No, that is, I completely agree, but I am just saying that these are, we should, unlike in ADS, I mean, in ADS3 CFT2, here if you like take this CFT, those, the super rotations, whether diffuse or this meromorphic super rotation, either one, they are really, what are they constraining as far as the bulk physics is concerned? Only the large distance part. So if you construct a dual theory with correlation functions, they are not going to reconstruct for you the finite energy bulk correlation functions, right? They possibly cannot, because they are not constraining from the bulk. I mean, this is the, at least we don't, I mean, this is something that we don't have a data point right now to say that they do construct. I give a theory for R and R plus R square, and these symmetries do not distinguish between them. So if they construct a bulk dual theory, what is it dual to? Is it dual to Einstein-Hilbert or Einstein-Hilbert plus higher derivative terms?
Yeah, so I think that's like it has an equivalent even in ADS CFT, right? I mean, because we don't understand the bulk string theory what it is.
Okay.
Like we still don't, I mean, like we don't have a clear statement of that, right?
No, but n equal to 4 super Young-Mills has more than just symmetries, right? That's why we are able to, in principle, the conjecture is that we get bulk physics. The dual theory, n equal to 4 super Young-Mills, it's not only going to construct the quantum gravity in the infrared, right? It's going to, I mean, the point is
it's going to construct everything.
Yeah.
But the asymptotic symmetries there are just the conformal symmetries.
But it is n equal to 4 super Young-Mills is not built only from asymptotic symmetries. It's not only built from asymptotic symmetries, right?
I'm distinguishing between. I'm saying that there are global symmetries.
No, I understand, but I'm saying that if you just look at the construction of n equal to 4 super Young-Mills, it does not only come from the symmetries of ADS5. No, but the reconstruction program, no, but I think we are on the same page. That's all I'm saying. I'm not saying any theory which will be dual to bulk quantum gravity will have these symmetries. I'm just saying that, but these are the symmetries of infrared. That's all I'm saying.
Yeah, I mean, what I'm not understanding is the distinction between symmetries of the infrared versus symmetries.
No, no. I think we are agreeing.
For super Young-Mills, the symmetries are just the symmetries, right? But you would say
Yes.
that they are in some sense asymptotic symmetries of the bulk.
But those symmetries do not just by themselves. If you take ADS5 CFT4, they don't constrain the bulk physics.
My point is that there is no distinction.
No.
Global symmetries versus asymptotic symmetries, I don't see a distinction.
There is no distinction. These are global symmetries of a dual theory for sure. But whether those global symmetries, however rich they are.
No, that the global symmetries are enough to fix the theory. That's not what I'm saying. I'm just saying global symmetries and asymptotic symmetries in the bulk are the same.
No. I was just putting it in context of reconstruction program. Right. That these global symmetries, are they enough? Even though the only reason I'm saying it is because they're infinite dimensional and there are, I mean, there is infinitely many super translations, infinitely many super rotations. So it's infinite square. So one may be tempted to think that they are really going to constrain our, if we reconstruct a dual theory which satisfies.
I would say the analog in ADS3 CFT2 is that knowing the Virasoro algebra does not fix the conformity.
Yes. It's an analog of that, yeah.
There was a claim by Strominger, Perry, and I think Strominger's student that these kind of infinite symmetries would fix the information paradox. What is the status of that?
No, that has not been, I think, very well developed, because as I was telling you yesterday, that even the statement is not well formulated. Because, to formulate this statement, okay, let me just give you the little bit of the idea of what they wanted to say. So the statement was the following, that if you consider if you just consider, let's say, some collapsing black hole, and now the point is that, okay, at some point this will evaporate, right, and then we will have some structure like this. This evaporation diagram, which I'm forgetting always. This was this stuff goes away, and then you get I don't know. Yeah, I think this one. That's the so black hole evaporated after some time, and so this what was supposed to be event horizon also disappeared, and we get empty space here. And now the statement was that, okay, suppose these infinitely many symmetries are symmetries of our theory, then you take all these charges in the past, let's say super translation and super rotation, and then all these charge in the past should be equal to charge in the future. But the charge in the future is charge on the horizon, for example, and charge at infinity. So now the point is that even when the black hole is evaporating, because the total symmetry is conserved, this information on the hair is not going to go away. So there is because there are infinitely many charges, there is infinite amount of information which is preserved on this on the horizon, and so that basically will remain. So that information is not lost inside because that's staying on the horizon, and because it's infinite, it may solve the information paradox. That was the hope. But to even make sense of this, even in a classical or semi-classical theory, we need to understand how to write this conservation law. So as we saw that, there are, in principle, there is a supertime generator here, and one on the horizon. And these two, as Karthik and Miguel show, that these two are antipodally identified. But there is no understanding of how to relate these two. And if you don't know how we can write a conservation also. So Hawking, Parrish, Strominger said we just take this to be F plus. But any calculations people have tried to do show that if you start with some foliation, then F is not equal to F plus. And the other point is more conceptual, which I think I was mentioning yesterday, that was explained to me by Miguel, that there is a puzzle about the super translation here as there. So let's forget conservation law, and let's say that I want to look at symmetries of horizon, which can, because it's a null manifold, like null infinity, in principle it can have some super translation and some super rotation. And if these symmetries exist, there will be hair here. So that means that for each, if I write F as some in terms of ILM, for each such ALM there is some charge here. But in classical GR there is a very robust theorem which has been proved rigorously called Price's law, which says that if you have perturbations which are along the horizon, then they always go as. So if you take if you have a perturbation which is ALM, and if V is the affine parameter on the horizon, then it always decays like this. But these are not static, they are only static for L equal to 0. But all the super translation here are static modes. So existence of this here seems to run in direct contradiction with the Price's law.
So you cannot excite them.
Yeah, and so I don't know how can they be? How can they even exist in classical gravity? Because this theorem is absolutely clean, and it's at the level of math GR rigor. So yeah.
Can you repeat that statement of Price's theorem?
Price's theorem is that if you perturb the horizon, then the perturbation, if it has a Lth mode, it will always decay at large V like this.
Oh, yeah.
But the super translation modes are always static.
This is kind of like a dynamical way in which hairlessness happens.
Exactly, how it settles down. If you perturb it, if you disturb horizon, in the end it settles down. And so, but super translation will tell you that all modes go like this, if the super hair existed. So how can these two statements be together true? But there have been many papers written on this, so maybe there is a catch, but no one has at least resolved it.
You are going to suggest references for.
Oh, yeah. So I'll just end with the references. So because I did not cover the conservation law for super rotation. So I will not give you all the references. Many of them you can find in the Strominger's book. But I would encourage you to take those conservation laws with a lot of caveat, because they are assuming that we don't have any infrared effect in 4 dimensions. So they are. This is this book on infrared gravity, infrared aspects of gauge theory and gravity. It's on archive.
Yeah, it's a book. It's an archive version.
Archive. It's basically a book is archive version. Yeah. So they give some formula for the super rotation charges, but they are derived assuming that your fields, you have no tail to the memory or anything. So they are not really true in 4 dimensions strictly. So at least as far as classical theory is concerned, I would encourage you to not treat them with care. And the more serious, we have attempted to do this more carefully in 4 dimensions. So there is one paper that we wrote with. Okay, I should first say in QED, Miguel and I, there are analog of all these statements in QED, which I had no time to get into. In QED, Miguel and I derived these charges, tried to derive these charges carefully in 2019. So I think this is in 2019 March on archive. And then for gravity, 4-dimensional super rotation charges, there is a paper with Andrea and her postdoc Sangmin. that we wrote I think in April this year, where we have tried to do the careful derivation of the superrotation charge in 4D. And then there's a paper that will come out maybe next, I hope by next month, which is, so this derivation is really in perturbative gravity. We have gravity coupled to scalar and we look at these charges. But the level at which we derive the super translation charge, that there is a charge at Scri minus and we use equation. At that level, so that's a full general relativity derivation for super translation charge. And there is a similar derivation for gravity which so I'm sorry, I'm writing a reference which is not even out yet, I apologize, with Mark Giller and Celine Zwickel, that will, hopefully it will come out in what is this, June. So this one would have a derivation at the level of this super translation charges we discussed in 4 dimensions for the super rotation, and such that in perturbative gravity it matches with what we found here. And this other paper that I wrote, which I don't quite understand, but I encourage you to look at it, which is the paper of this came out last year. They have 2 papers actually, 2020. If you look for logs of theorem and asymptotic symmetries with these authors, you will find 2 papers. Okay, so as far as the other symmetries are concerned, maybe this you may find this useful. So celestial holography, Partha can say much more. I think that it has been able to use all these symmetries, the super translation certainly, and this other one, super rotation, but assuming we are having a very fast fall off, in the sense what we call tree level amplitudes in asymptotic, and they're able to derive using these symmetries. I don't know. It's a CFT statement, and I think as Shamik and Partha have done that, construct amplitudes at tree level like MHV and using only these symmetries, nothing else. But their symmetries are far more refined, I must say. They are not these. So what, I don't know why I'm speaking, he should speak, he is the founder. So what they realized was that at the level of this dual theory, these symmetries can be split into some currents which are more refined. And these currents actually, if you use these currents, then their identity can actually give you, reconstruct a class of tree level amplitudes without any knowledge of the theory. And these currents are very remarkable in the sense we don't see them in classical theory. In the sense classical theory, only these charges are conserved, right? But I think that once you go to this dual theory, there are these refined currents that are conserved. There is more, much more. I think maybe he can say more. My knowledge is limited. So is that correct statement or is it not? Yeah. So there are these for each, like for super translation charge, there are like 3 currents. There are 3 currents. So each charge splits into 2 currents. So each charge splits into 2 currents, and then super rotation 3. So so now you want to construct celestial correlators using these currents, and that they are really more refined. So maybe they constrain actually bulk physics also. Yes, they are able to write down MHV and maybe NMHV. MHV so far using only these currents. That's quite remarkable. Yeah.
So these are amplitudes in Einstein theory. But if you pretended that these symmetries are non-perturbative, then you get a useful theory.
No, they could constrain.
No, so I think the logic is the opposite, that you just start with these currents and you ask, okay, I want to write down correlators on a sphere for which this identity of these currents are satisfied, and they're able to write down some correlators. That's first statement, and then it turns out that some of them are actually just MHV amplitudes, tree level amplitudes for Einstein gravity. So they go other way, like they don't know what the bulk theory is. They just want to write down celestial correlators for boundary gravitons, if you want.
If we go to higher point functions, that should be able to distinguish the Einstein theory from higher.
I think the loop, if you go to loop amplitudes in the celestial, clearly the loop effects will take into account higher derivative terms, right? But I don't know how much progress. Symmetry may also change, you don't know.
No, for example, if there was an R-cube term, your 3-point function would actually change.
But why is that? Because super translation is still a symmetry, superposition is still a symmetry, because they don't depend on this idea. Oh, okay, but no, but only these ones, they will remain. But your MHV you are able to create only from these, right? MHV you are able to construct.
I mean, like
Yes.
if you go to RQ, then all kind of amplitudes, all kind of densities are possible, right?
Yes.
Then you cannot only talk about positive density software.
Yeah.
This current that we had, only for image, they came from the positive density software. Because
But soft theorem is same for R cube also, na?
but then you don't know the full symmetry as well, right? You have positive as well as negative density software.
Okay.
So you don't know the full algebra.
I see. So I think they are more refined because they are able to distinguish, you see, between R cube and R, which these standard garden variety BMS don't do.
Any other questions? If not, let's thank Alok for a beautiful lecture.